The American test pilot pushed the throttle forward on the morning of May 10, 1945, at Freeman Field, Indiana. The twin Jumo 004 turbojets spooled up with a sound unlike anything in the Allied arsenal, a high-pitched scream that made the Pratt and Whitney radials on nearby Thunderbolts sound like farm equipment. Colonel Harold Watson had flown 43 different aircraft types during the war, but nothing had prepared him for what the captured Messerschmitt Me-262 was about to show him. Within seconds of rotation, the German jet fighter achieved a climb rate that defied every assumption American engineers held about what was possible in 1945. But hidden in the fuel quantity gauge was a number that would explain why this technological marvel had failed to change the war's outcome. 30 minutes. Just 30 minutes of fuel capacity at combat power. The question wasn't whether Germany had built the world's first operational jet fighter. The question was whether they had built a weapon or merely an engineering demonstration, a 540-mile-per-hour sprint toward inevitable flameout. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Me-262 that Watson flew that spring morning had traveled a long road to Freeman Field, designated with the Werk number, or factory number, 500210. This particular aircraft had been assembled at the Messerschmitt plant in Leipzig in March of 1945, painted in the mottled green and gray camouflage of Jagdverband 44, and flown exactly 3 operational sorties before Germany's collapse. When elements of the U.S. Ninth Army reached the Lechfeld airfield complex south of Augsburg on April 28th, they discovered what intelligence officers initially dismissed as a clerical error in the inventory reports: 47 intact Me-262s in various states of assembly, along with technical manuals, maintenance logs, and fuel consumption data that would soon make their way to Wright Field, Ohio. The Allied intelligence community had known about German jet development since 1943, when reconnaissance Spitfires photographed unusual twin-engine aircraft at the Rechlin test facility. British analysts noted the absence of propellers and the peculiar engine nacelles slung beneath swept wings, but photographic interpretation could only reveal so much. The first hard intelligence came from a Luftwaffe defector in March of 1944, a maintenance officer who provided technical drawings suggesting turbine engines producing thrust ratings that seemed physically impossible. Even after the first combat encounter in July of 1944, when Me-262s attacked a formation of British Mosquito reconnaissance aircraft, Allied fighter pilots returned with descriptions that sounded like fever dreams, enemy fighters overtaking them at speeds they estimated at well over 500 miles per hour, executing attacks and breaking away before their gun cameras could track the motion. What the Allied pilots didn't know, what couldn't be understood from brief visual contact or gun camera footage, was that every one of those lightning-fast attack runs was occurring against a countdown clock. The Junkers Jumo 004B turbojet, the engine that gave the Me-262 its revolutionary performance, consumed fuel at a rate that would have seemed incomprehensible to pilots trained on piston engines. A Rolls-Royce Merlin engine in a P-51 Mustang burned roughly 70 gallons per hour at cruise power, giving the American fighter a combat radius exceeding 400 miles with drop tanks. The Jumo 004B, by contrast, consumed nearly 500 gallons per hour at full military power. The Me-262's internal fuel capacity of 210 gallons, split between fuselage tanks and 2 underwing tanks, translated to roughly 30 minutes of operation at combat settings, or about 50 minutes at reduced throttle for transit. This wasn't a design flaw that could be fixed with engineering iteration. It was a fundamental limitation of early jet propulsion technology, colliding with the material realities of 1945 Germany. The kerosene-based J2 fuel required for the Jumo engines was derived from coal through the Fischer-Tropsch process at synthetic fuel plants that Allied bombing had reduced to a fraction of their designed capacity. By early 1945, Luftwaffe logistics officers were allocating jet fuel in quantities measured by individual sorties rather than operational campaigns. A Me-262 unit received enough fuel for perhaps 3 to 5 missions per aircraft per week, assuming the fuel trucks could navigate the bomb-cratered roads to reach the dispersed airfields where the jets operated. The pilots selected to fly the Me-262 understood they were operating the most advanced fighter aircraft in the world under conditions that made sustained combat operations nearly impossible. Lieutenant Franz Schall, an ace with hundreds of missions in conventional fighters, described his first jet sortie in his combat log as 10 minutes of climbing to altitude, 15 minutes of patrol, and a constant mental calculation of when I needed to turn back before the engines flamed out over enemy territory. The standard tactical profile for Jagbarbahn 44, the elite jet unit commanded by Lieutenant General Adolf Galland, involved scrambling on alert when Allied bomber formations were detected by the surviving radar network, climbing to 30,000 feet at maximum power, executing a single high-speed attack pass through the bomber formations, and immediately descending to conserve fuel for the return to base. There was no provision for extended combat maneuvering, no fuel margin for pursuing damaged bombers, and no possibility of the kind of sustained dogfighting that had characterized air combat earlier in the war. American intelligence officers examining the captured aircraft at Lechfeld found maintenance logs that told the story more clearly than any tactical report. Aircraft 500210 had logged 12 flight hours and 43 minutes across its entire operational life. The average sortie duration was 27 minutes. The longest single mission, a patrol on April 2nd during a period when Allied bomber activity was light, lasted 41 minutes and ended with an emergency landing at an auxiliary field after both engines flamed out on final approach due to fuel exhaustion. The pilot, whose name appeared in the logbook only as Obolt Müller, had walked away from a dead-stick landing in the world's most advanced fighter because he had tried to extend his patrol time by 9 minutes. When the technical intelligence team from Wright Field arrived at Lechfeld in early May, their primary objective was to select the most intact examples for shipment to the United States under Operation Lusty, the code name for the seizure of German aeronautical technology. Captain Eric Brown, the Royal Navy test pilot who had evaluated more captured enemy aircraft than perhaps any pilot in the war, was attached to the American team specifically to assess the Me-262. Brown had flown everything from the Focke-Wulf 190 to experimental rocket-powered interceptors, and his reports carried weight in Allied intelligence circles. His initial assessment of the Me-262, written after a ground examination but before any flight testing, noted, "The aircraft represents a genuine revolution in fighter design. The question is whether Germany possessed the industrial capacity to make this revolution operationally relevant." The answer to Brown's question was contained in documents the intelligence team found in the Messerschmitt administrative buildings at Lechfeld. Production records showed that from the beginning of serial manufacture in June of 1944 through Germany's surrender, approximately 1,400 Me-262s had been manufactured. Of these, only 200 to 300 ever reached operational units. The remainder were destroyed in Allied bombing raids on factories and airfields, lost to mechanical failures during delivery flights, or simply abandoned due to lack of fuel. Even more revealing were the fuel consumption projections prepared by Luftwaffe logistics staff in January of 1945. The these documents calculated that maintaining 100 Me-262s in sustained operations would require the entire monthly output of Germany's remaining synthetic fuel plants, leaving nothing for the thousands of conventional fighters, bombers, and training aircraft that still formed the bulk of the Luftwaffe. The strategic impossibility of the Me-262 program became clear when American analysts cross-referenced captured production data with ultra-intercepts. The decoded Luftwaffe communications that had given the Allies insight into German operations throughout the war. In March of 1945, with jet production still continuing at underground factories, Luftwaffe High Command had issued orders grounding all Me-262 units for 3 days due to complete exhaustion of J-2 fuel stocks. The jets literally sat on their dispersal areas, fully armed and ready for combat, while American heavy bombers struck targets in broad daylight overhead. When fuel deliveries resumed, the available quantity permitted only the most critical defensive sorties. Pilots were briefed that any combat resulting in fuel expenditure beyond the planned mission profile would likely result in loss of the aircraft, not to enemy action but to fuel starvation during the return flight. This was the context that Colonel Harold Watson carried with him when he climbed into the cockpit of aircraft 500210 on that May morning in Indiana. Watson had been selected for the Freeman Field Test Program specifically because of his experience evaluating German aircraft. He had flown captured Focke-Wulf 190s and Messerschmitt Bf 109s, and had written detailed reports on their handling characteristics compared to American fighters. But the briefing he received before his first Me-262 flight was unlike any other aircraft checkout. The German test pilots who had been brought to the United States to assist with the evaluation, former Luftwaffe personnel who had agreed to cooperate in exchange for guaranteed treatment as technical specialists rather than prisoners of war, emphasized one point above all others. Every minute of flight time was borrowed against an inflexible fuel budget that permitted no margin for error. The pre-flight inspection revealed engineering solutions that existed nowhere else in aviation at that time. The Jumo 004B engines were unlike any power plant Watson had encountered. Instead of pistons and crankshafts, the core of each engine was a 9-stage axial compressor that forced air into combustion chambers where fuel was ignited in a continuous process, with the expanding gases driving a turbine that powered the compressor. The result was a power-to-weight ratio that made piston engines look like antiques. Each Jumo 004B weighed approximately 2,000 pounds and produced roughly 1,900 pounds of thrust, giving the Me-262 a thrust-to-weight ratio unmatched by any Allied fighter. But this revolutionary efficiency in power generation came with a cost measured in fuel consumption that exceeded anything in Watson's experience. The German technical advisor who walked Watson through the engine start procedure explained the fuel system with precision of someone describing a precision timepiece. The main fuel tanks held 190 gallons, with an additional 20 gallons in a small reserve tank. At full throttle, what the Germans termed Vollgas, the two engines together consumed approximately 8 gallons per minute. At cruise power settings, consumption dropped to roughly 5 gallons per minute. The mathematics were simple and unforgiving. 30 minutes at full power, 40 minutes at moderate power, or some combination that always ended with the same conclusion. You must land with fuel remaining, the advisor said in accented English. The Jumo does not restart in flight if it flames out. You become a glider with very poor gliding characteristics. Watson's first flight lasted 23 minutes. The acceleration during takeoff was unlike anything he had experienced in 4 years of test flying. The Me-262 lifted off after a ground roll of roughly 800 yards and climbed to 10,000 feet in less than 4 minutes. At altitude, Watson advanced the throttles to 90% power, the setting recommended for combat maneuvering, and watched the airspeed indicator climb past 500 miles per hour, with the nose barely above the horizon. The Focke-Wulf 190 that he had flown the previous week could reach perhaps 410 miles per hour in level flight at full power. The P-51 Mustang, the fastest fighter in American service, topped out around 440 miles per hour. The Me-262 was operating in a different regime of flight entirely. But even as Watson explored the Me-262's performance envelope, his eyes kept returning to the fuel gauges. The needles were moving with visible speed, each minute of flight consuming resources that translated directly into shrinking options for the return to base. After 15 minutes of flight testing, including several high-speed runs and climbs to assess handling characteristics, Watson reduced power and began a descent back to Freeman Field. He landed with approximately 70 gallons remaining, enough for perhaps 12 more minutes of flight. The post-flight debriefing focused less on the aircraft's remarkable speed than on the operational implications of its fuel consumption. You could intercept any Allied bomber formation in Europe, Watson told the assembled engineers and intelligence officers, but you'd have time for exactly one attack pass before fuel considerations forced you to disengage. And if that pass didn't achieve results, you'd accomplished nothing except burning fuel Germany didn't have. The technical analysis that followed Watson's initial flights revealed why German engineers had been unable to solve the fuel consumption problem. The Jumo 004B operated at turbine inlet temperatures exceeding 1,300 degrees Fahrenheit, temperatures that pushed the metallurgical limits of materials available in 1945. Higher efficiency would have required higher compression ratios and higher temperatures, which demanded alloys containing nickel and chromium that Germany's blockaded economy could not provide in sufficient quantities. The British, working on their own jet engine development in parallel, had access to specialized alloys through their supply lines to North America and were already testing engines with significantly better fuel consumption characteristics. But those British engines wouldn't reach operational squadrons until 1946. The Germans had achieved operational jet flight first, but they had done so with engines that represented the absolute limit of what their constrained industrial base could produce. The fuel consumption data that American engineers extracted from the captured Me-262s told a story about the entire German war effort in microcosm. Luftwaffe planning documents from late 1944 showed that German strategists had calculated they needed at least 500 operational jet fighters to make a meaningful impact on the Allied strategic bombing campaign. 500 Me-262s flying defensive sorties could potentially inflict losses severe enough to force a reduction in American daylight bombing operations. But sustaining 500 jets in combat required fuel allocations that exceeded total German synthetic fuel production, even before Allied bombing began systematically destroying the Fischer-Tropsch plants in the summer of 1944. The program that was supposed to restore German air superiority was consuming resources faster than the collapsing German economy could provide them. Lieutenant Franz Schall's combat log, which American intelligence officers found among captured documents at Lechfeld, provided a pilot's perspective on these strategic impossibilities. Schall had been an instructor pilot before transitioning to jets, and his entries reflected both professional appreciation for the Me-262's capabilities and frustration with its operational constraints. An entry from March 18, 1945, described a mission where his 4-aircraft formation scrambled to intercept American B-17s attacking targets near Munich. The jets climbed to intercept altitude in 6 minutes, a climb rate that would have taken conventional fighters 20 minutes or more. But by the time they reached the bomber formation, fuel considerations allowed only a single attack pass. Schall's aircraft damaged one B-17 with 30mm cannon fire, but the bomber remained in formation and continued to its target. Returned to base with warning lights indicating fuel exhaustion, Schall wrote. Total flight time, 29 minutes. 1 bomber damaged. 300 gallons of irreplaceable jet fuel expended. The mathematics do not favor us. The American test program at Freeman Field eventually expanded to include multiple captured Me-262s, each providing additional data on the aircraft's capabilities and limitations. Captain Eric Brown flew aircraft 500210 in June of 1945 and filed a report that would become one of the definitive Allied assessments of German jet technology. Brown noted that the Me-262's speed advantage over Allied fighters was so substantial that conventional air combat tactics were essentially irrelevant. No Allied piston-engine fighter can catch a Me-262 if the German pilot chooses to disengage, Brown wrote. But equally, the Me-262 cannot sustain combat long enough to exploit this advantage in any meaningful operational sense. The aircraft is a technological triumph married to a logistical catastrophe. The fuel limitation shaped every aspect of Me-262 operations in ways that pilots trained on conventional fighters found deeply counterintuitive. In a piston-engine fighter, fuel management was a matter of planning for the mission duration with reasonable reserves. In the Me-262, fuel management was the primary tactical consideration that overrode all others. Luftwaffe Tactical Doctrine for jet operations explicitly stated that pilots should break off combat and return to base when fuel quantity fell below 100 gallons, a reserve that provided roughly 15 minutes of flight time. This meant that effective combat time, after subtracting fuel required for taxi, takeoff, climb to altitude, and return to base, was typically between 10 and 15 minutes. German fighter pilots, many of whom had flown hundreds of combat missions in Bf-109s and Fw-190s, found themselves operating the world's most advanced fighter under constraints that reduced them to making single attack passes and fleeing before Allied escorts could even react. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The strategic bombing campaign that the Me-262 was designed to counter continued with barely any interruption throughout the jet's operational deployment. American intelligence analysts, examining captured Luftwaffe records after the war, calculated that Me-262s shot down approximately 100 to 150 Allied aircraft between July 1944 and May 1945. This was not an insignificant number. Each bomber lost represented 10 aircrew and a multi-million-dollar aircraft. But during that same period, American and British bombers flew more than 200,000 sorties over Germany, dropping over 800,000 tons of bombs. The mathematical reality was that Germany would have needed to shoot down thousands of Allied bombers to meaningfully impact the strategic bombing campaign, and the fuel consumption characteristics of the Me-262 made such attrition rates physically impossible to achieve. The test flights at Freeman Field continued through the summer of 1945, with American engineers systematically documenting every aspect of the Me-262's performance. Maximum level speed at altitude was confirmed at 540 miles per hour, more than 100 miles per hour, faster than the fastest Allied fighter in operational service. Rate of climb exceeded 4,000 feet per minute, nearly double that of contemporary American fighters. Ceiling was above 40,000 feet, well above the altitude where most Allied bombers operated. In every measurable category of performance, the Me-262 was superior to anything the Allies could field. And in the category that mattered most, combat endurance, it was inferior to every piston-engine fighter in service. Colonel Watson's final report on the Me-262 evaluation program, submitted to Army Air Forces headquarters in August of 1945, concluded with an assessment that captured the paradox of German jet development. The Me-262 represents a genuine technological breakthrough, Watson wrote. Germany succeeded in fielding an operational jet fighter before any Allied nation. But the aircraft's fuel consumption characteristics, combined with Germany's collapsing fuel production infrastructure, meant that this technological advantage could never be translated into operational advantage. The Germans built a fighter that could outrun and outclimb anything we had, but they couldn't fuel it in sufficient numbers to matter. The fuel consumption data that doomed the Me-262's operational effectiveness was not a secret to German planners. Documents captured at the Messerschmitt Design Bureau showed that engineers had identified the fuel problem during initial testing in 1943 and had proposed multiple solutions. One proposal involved enlarging the internal fuel tanks to increase combat endurance, but this would have added weight that reduced the aircraft's performance advantages. Another proposal suggested developing drop tanks that could be jettisoned after use, but manufacturing capacity for such tanks was non-existent in late-war Germany. A third proposal, raised by Luftwaffe logistics officers, simply stated that jet fighter operations should be suspended until fuel production could be increased to sustainable levels. This proposal was rejected by High Command, who believed that even limited jet operations would have propaganda value and might inflict sufficient losses on Allied bombers to justify the resource expenditure. The reality of Me-262 operations bore little resemblance to the propaganda image that German leadership tried to project. Jagdverband 44, the elite unit formed specifically to demonstrate the jet's combat potential, operated under conditions that would have been unthinkable earlier in the war. Aircraft were dispersed to concealed locations in forests and along highways to protect them from Allied bombing. Fuel trucks, when they arrived at all, were escorted by armed guards because the kerosene-based J2 fuel had become more valuable than gold in Germany's collapsing economy. Pilots conducted pre-flight inspections, knowing that the fuel in their tanks represented a larger share of Germany's remaining resources than the aircraft itself. The psychological burden of operating under such constraints was evident in pilot accounts from the final months of the war. Oberleutnant Heinz Baer, one of the Luftwaffe's most successful aces with more than 200 victories, flew the Me-262 in the final weeks before Germany's surrender. His post-war interviews with Allied interrogators described missions where tactical decisions were entirely subordinated to fuel considerations. "We would scramble when American bombers were detected," Baer recalled. "We would climb to altitude at maximum power, knowing every second of full throttle was reducing our combat time. We would make one attack pass, usually targeting bombers that had already been damaged by flak, because they were slower and easier to catch. And then we would descend immediately to conserve fuel for landing. If we saw Allied escort fighters positioning for an intercept, we simply accelerated away. We could outrun any Mustang or Thunderbolt, but we couldn't afford to maneuver with them. The fuel wouldn't permit it." The Americans examining the captured aircraft at Freeman Field found evidence of just how desperate the fuel situation had become in the final months of the war. Maintenance logs for several Me-262s showed that aircraft had been flown on missions with fuel loads deliberately reduced below standard capacity, because even the standard load was unavailable. One aircraft had been dispatched on an intercept mission with only 140 gallons of fuel, roughly 20 minutes of flight time at combat power. The pilot had executed a single attack pass against a formation of B-24s, claimed no hits, and landed with fuel quantity so low that both engines quit during the taxi back to the dispersal area. The maintenance log noted simply, "Mission accomplished. Aircraft recovered. No fuel available for further operations." The technical intelligence gathered from the Me-262 program influenced American jet development in ways both obvious and subtle. The immediate lesson was that early jet engines consumed fuel at rates that required fundamental rethinking of fighter tactics and logistics. But the deeper lesson was about the relationship between technological advancement and industrial capacity. Germany had achieved a genuine breakthrough in aeronautical engineering, but they had done so in an economic context that made it impossible to exploit that breakthrough. The Americans, studying the captured jets at Freeman Field and Wright Field, recognized that their own jet development programs would need to be matched with fuel production infrastructure capable of sustaining operations. There was no point in building 500 jets if you couldn't fuel them. The Me-262 that Colonel Watson flew that May morning in Indiana now sits in a museum, one of the handful of captured examples that survived the post-war period. The placard describes it as the world's first operational jet fighter and notes its impressive performance specifications. Maximum speed, 540 miles per hour. Rate of climb, 4,000 feet per minute. Armament, 430mm cannon. What the placard doesn't emphasize, what visitors walking past the restored aircraft rarely consider, is the fuel capacity notation in smaller text, 210 gallons. Endurance at combat power, 30 minutes. That 30-minute figure represents perhaps the most important lesson of the Me-262 program. Germany had solved the engineering problem of jet propulsion before any Allied nation. They had designed an airframe that could exploit the power of turbine engines. They had trained pilots to fly it and developed tactics to employ it. But they couldn't solve the fundamental problem of thermodynamics and chemistry that made early jet engines consume fuel faster than their collapsing industrial base could produce it. The result was an aircraft that could achieve 540 miles per hour, but couldn't stay airborne long enough to matter. The American pilots who flew the captured Me-262s in the summer of 1945 came away with a complex understanding of what German technology had achieved and where it had failed. The aircraft was genuinely revolutionary. The performance measurements were not propaganda or exaggeration. But performance without sustainability was merely a technical demonstration, not a weapon. The Luftwaffe had fielded an aircraft that could outfly anything the Allies possessed, but they had done so at a moment when Germany's ability to sustain any kind of advanced operations was collapsing under the weight of strategic bombing and resource exhaustion. Franz Schall, the Me-262 pilot whose combat log documented the frustration of flying a technological marvel under impossible constraints, did not survive the war. He was killed in April of 1945 when his jet suffered an engine failure on takeoff, not due to combat damage, but due to a turbine blade failure caused by substandard materials forced into production when higher quality alloys became unavailable. His last logbook entry, written 2 days before his death, noted that his unit had received fuel for only 2 missions that week. "The aircraft are capable," he wrote. "The will is present. The fuel is not." The story of the Me-262 is often told as one of German technological superiority squandered by poor strategic decisions or leadership failures. But the fuel consumption data tells a different story, one about the limits of technological innovation when divorced from industrial capacity. The Germans didn't fail to recognize the fuel problem. They didn't fail to understand its implications. They simply couldn't solve it within the constraints of their collapsing economy and the relentless Allied bombing campaign that destroyed their synthetic fuel plants faster than they could be rebuilt or dispersed. The Me-262 could achieve 540 miles per hour, but Germany couldn't produce enough fuel to make that speed operationally relevant. When Colonel Watson submitted his final evaluation report, he included a calculation that captured the essential paradox. A single Me-262 consumed enough fuel in one 30-minute combat sortie to keep 5 piston-engine fighters airborne for the same duration. From a purely tactical perspective, the jet's superior performance might have justified this exchange ratio. But from an operational perspective, in an economy where fuel was scarcer than trained pilots or airframes, the calculation was devastating. Germany could field 5 conventional fighters for every one jet, and those conventional fighters could patrol longer, engage more flexibly, and land with fuel reserves rather than warning lights. The Me-262's speed made it tactically superior in every engagement. Its fuel consumption made it strategically irrelevant. The captured aircraft that American engineers examined so carefully at Freeman Field and Wright Field provided a kind of autopsy report on German war production. Every aspect of the Me-262 showed evidence of both remarkable engineering and desperate improvisation. The engines used bearings made from substitute alloys because proper bearing steel was unavailable. The fuel tanks were manufactured from steel rather than aluminum, because aluminum had been diverted to other programs. Even the paint scheme reflected material shortages. Late production aircraft used whatever pigments were available, resulting in camouflage patterns that varied from one aircraft to the next based on what the paint shops had in stock. But the fuel consumption remained constant across all examples, because it was determined by the fundamental physics of the engine design and the chemistry of the available fuel. The Jumo 004B consumed approximately 8 gallons per minute at full power, because that's what a turbojet with that compression ratio and turbine inlet temperature required to produce 1,900 pounds of thrust. No amount of engineering refinement could change that basic equation without access to better materials for higher temperature operation or more time for development that Germany's strategic situation no longer permitted. The test pilots at Freeman Field eventually stopped flying the captured Me-262s by late 1945. The aircraft had yielded all the intelligence value they could provide, and the Jumo engines, which had limited service, lives even under ideal conditions, were wearing out. The Americans were already testing their own jet designs, incorporating lessons learned from the German program, but building them within an industrial infrastructure that could actually sustain operations. The future of jet aviation would be built by nations that could fuel it, not by the nation that had achieved it first under impossible constraints. The final flight of aircraft 500210 occurred on November 3, 1945. The pilot, whose name was not recorded in the maintenance log, flew for 18 minutes, conducted several high-speed passes for the benefit of film cameras documenting the program, and landed with the engines showing early signs of turbine degradation. The aircraft was then moved to storage, eventually making its way to the museum where it remains today. The Jumo engines never ran again. They had consumed their final gallons of fuel, and there was no operational requirement that justified keeping them serviceable. 79 years later, the Me-262 remains one of the most analyzed aircraft of World War II. Historians debate whether earlier deployment could have altered the war's outcome, whether different tactical employment could have made the jets more effective, whether German industrial priorities should have been different. But the fuel consumption data admits no debate. 210 gallons of fuel, 30 minutes at combat power, The mathematics were immutable, and they spelled out a conclusion that no amount of technological brilliance could overcome. Germany had built the future of aviation, but they couldn't afford to fly it. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.